Assignment 3 is posted online, and so are the problems for Chapter 3. So they're posted on the Moodle site for this week, and I'll do an example from the notes, and then we'll work on the assignment together. We'll do some of the examples from that problem set, and we'll get you started on the ones that you have to hand in and answer any questions. So assignment 3 is due next Friday. So let me start with a quick review of what we did on Tuesday. The main thing that we found is this new thing called the Lagrangian. So we found that we could describe a single particle we can describe the motion of a single particle using what's called the Lagrangian. This Lagrangian L is a scalar function, and it's defined to be T minus V. So for a single particle, T is the kinetic energy. And in the next lecture, we'll just see that this trivially extends for multiple particles to be the total kinetic energy. And then V is the potential energy. So by simply writing out what the kinetic energy and the potential energy are in terms of generalized coordinates, then the equations of motion are given by what's called the Euler-Lagrange equation. The Euler-Lagrange equation is for each degree of freedom, you have d by dt of di L by di Qj dot minus di L by di Qj equals 0. And it's equal to 0 if all forces are monogenic. And that generally means that the forces are conservative. We also introduced the generalized potential. And a generalized potential is just a more general case of a potential that gives rise to a conservative force. So a generalized potential gives rise to a generalized force given by d by dt of di u by di Qj dot minus di u by di Qj. So this first of all, you can see that the form of this, of how you go from the potential U to the force Q, is exactly the same form mathematically as the Euler-Lagrange equation. Of course, that's on purpose. That's so that you can include this potential U inside of the Lagrangian L. So what makes this a generalized potential is that first term with the d by dt. If it was just the minus di u by di qj, then that's very much like a standard potential for a conservative force, such as gravity or the Coulomb force, or the electric potential. If there's any questions about this? And we'll do many example applications of it. So let me do one example from the notes, and then we'll move on to sort of the tutorial part of the lecture. We'll go through examples from chapter 3. So let me do the example from the notes, which is example 4.2. So example 4.2, what we really want is the Lagrangian for a particle with electric charge E, so like an electron, velocity v, and then moving in a region with electric field capital E vector and magnetic field capital B vector. Okay. So from Newton's second law, we know that we should have an equation of motion that's something like ma equals E times V cross B with the Lorentz force plus E, the charge, times the electric field, right? So that's the Lorentz force for the magnetic field, that's the electric force. So whatever description we have, hopefully will give us that equation of motion. And so everybody's familiar with electromagnetism, right? You've heard of the vector potential. So, thanks for the approval. That's a good way of doing it. So let me just recall from electromagnetism that the magnetic field B can be found by taking the curl of the what's called the vector potential A. And then the electric field E is given by minus grad phi minus di A by di T. So this is basically part of Maxwell's equations, right? So phi is the electric potential. And the dA by dt is the Faraday's law, right? Changing magnetic field gives rise to an electric field. All right, so I'll take these as given. So it's one particle. So we have 3 degrees of freedom. And so we'll choose Cartesian coordinates to describe our particle. So x, y, and z. Now what I'm going to do is I'm going to introduce the correct form of the generalized potential for the situation, and then we'll show that it gives rise to the correct equations of motion, which we wrote out using Newton's second law. Okay. So for electromagnetism, the generalized potential, I'm going to call it V instead of U. Is given by the charge of the particle times the electric potential minus the charge of the particle times the vector potential dotted with the velocity vector v. And so we'll show that this works. Because right now it looks a little bit arbitrary. So if I write this out in Cartesian coordinates, that's E times phi, and remember phi and A are both functions of space. And then if I write out the dot product explicitly, then I have AX VX plus AY VY plus AZ VZ. All right, that's just writing out the dot product in Cartesian coordinates. And so remember, this is the generalized potential, so it must have something to do with energy. So we can at least recognize the first term as electric potential energy, right? The charge of a particle times the value of the electric potential is the potential energy. It's just like mgh, right? For gravity. It's the same thing for electromagnetism. So given this form of the potential, let's go and find out what the generalized force is equal to that comes from this potential. So consider Qj from our generalized potential V. So remember, the force, the generalized force that comes from a generalized potential is d by dt of di V by di Qj dot minus di V by di Qj. And so let's do this. So let's evaluate Qj, or capital Qj, for the degree of freedom Qj, lowercase qj, is equal to x. So remember, the lowercase qj's there in the equations are the degrees of freedom. We have 3 degrees of freedom, so Q1 is x, Q2 is y, and Q3 is z. So what we want is Qx, right? So Qx is going to be d by dt of di v by di x dot minus di v by di x. Let me rewrite v here just so we don't have to keep flipping back and forth. V was equal to e phi minus e times ax dx plus ay dy plus az vz. So Qx is going to be d by dt of di v by di x dot. So Vx is x dot, right? Vy is y dot, and Vz is z dot. So di v by di x dot is equal to minus e, and the only term that has an x dot is ax. And then it's minus di v by di x. So now both potentials, phi and a, can depend on position, right? They're fields, so they're different in different positions in space. So d by dx of both phi and a are non-zero. So we have first d by dx of the first term, so that'll be minus e d phi by dx, or maybe I'll just keep them as partial derivatives. And then it's minus di v by di x, so all the next terms with the a's in them are going to be positive. So then it's plus e x dot di ax by di x plus e y dot di ay by di x plus e z dot di az by di x. So that first term is minus e d by dt of ax. So we need to know what d by dt of ax is. So d by dt of ax, so ax potentially depends on x, y, z, and t, right? So if I do the chain rule of d by dt of ax, and remember this is the total derivative. So let me just note that ax is a function of x of t, y of t, z of t, and t, right? So if I do the total derivative, this is something we did I think in the first lecture, then I have to break it out into all of the terms. So I have a di ax by di x x dot plus di ax, sorry, by di y dot plus di ax by di z dot, and then plus di ax by di t. So I'll place that into now my equation for Qx. So Qx, now the first term was minus e times this d by dt, which we just wrote, right? So it's minus e, and then I have di ax by di x, x dot, plus di ax by di y, y dot, plus di ax by di z, z dot, plus di ax by di t. And then I have a minus e di phi by di x. And then I have the last three terms plus e x dot di ax by di x plus e y dot di ay by di x plus e z dot di az by di x. So I think I did that correctly. It's easy to get mixed up because there's a lot of x's and y's and ax's and so forth, but I think that's correct. So now let me examine this. So first of all, if we look at the x dot term, right, I have a minus e di ax by di x, x dot, right? This term here, that cancels this term here. Right, so the final answer is not going to have any x dots in it. So let me first collect the term that don't have any y dots or z dots in it. So that's this term and this term. We're going to write them out first. So let me factor out the e. Then I have minus di ax by di t minus di phi by di x. Then let me collect the terms in y dot. So I have ey dot. I have two terms. I have this positive term over here and a negative term up here. So the terms in y dot, we have a di ay by di x. Can you guys keep it down? Minus di ax by di y. I'll do the same thing for the z dot term, which are the remaining terms. I have e z dot di az by di x minus di ax by di z. So recall that the electric field E is given by minus grad phi minus di A by di T. So the x component of that is minus di phi by di x minus di ax by di t, which is exactly the first term. So qx is equal to, the first term is e the charge times the x, well, I shouldn't put an arrow there, times the x component of the electric field, right? Now, the second term, I have E y dot. If I look at di ay by di x minus di ax by di y, that is in fact the x component of the magnetic field. Right, that is the x component of the curl of A. And then similarly, the second term is Ez dot by. So this term here is equal to minus curl of A y component. And if I go even further, I can note that the last two terms are just the cross product of the velocity vector and the magnetic field. So this generalized force in the end becomes the charge times the x component of the electric field plus the charge times v cross b and the x component of that. And so of course, that is the x component of the Lorentz force. So similarly, if we do Qy, we'll find the y component of the Lorentz force. So that would just be E times Ey plus E times V cross B y component. And similarly for Qz, you would get the Z component of the Lorentz force. So the generalized potential given by V equals E phi minus E times the dot product of A and B, the velocity, gives the correct expression for the Lorentz force. So this potential is adequate for describing the motion of a particle in an electric and magnetic field at once. So we can now write out the Lagrangian, which is T minus V. And so the kinetic energy of a particle in Cartesian coordinates in free space is a half mx dot squared plus y dot squared plus z dot squared. And then our potential is minus E phi, then plus E A dot B. So the equations of motion are given by applying the Euler-Lagrange equation. So we would do d by dt of di L by di qj dot minus di L by di qj equals 0, where qj is equal to x, y, and z. So let me plug that in to for x. So we've actually already done d by dt of di v by di qj dot minus di v by di qj. That gave us qx, right? So what we need now is for x, we need to do d by dt of di capital T by di x dot. So that's d by dt of, if I do the di by di x dot of the kinetic energy term, that's simply mx dot, right? And if I do d by dt of that, I get mx double dot. T does not depend on x, right? So di t by di x equals 0. And so if I plug it all in, I have d by dt of di by di qj dot, or x dot, sorry, of t minus v minus di by di x of t minus v, but in this case di by di x of t is 0. And we've already evaluated the d by dt di by di x dot of v and di by di x of v. And so this will give us mx double dot equals the term that we have here. Which is as expected. Okay, and of course you get the same thing for y and z. Any questions about that? Okay, so if there's no questions, then please open up the problem set for Chapter 3, which is on the Moodle website. And so this is an assignment on virtual work and D'Alembert's principle. So let me remind you of virtual work and D'Alembert's principle. So the principle of virtual work is that for static equilibrium, we have that the sum of the virtual work done by n forces, Fi, is equal to 0. And D'Alembert's principle extended this to dynamics, and it gave us that d by dt of the kinetic energy of the system by qj dot minus psi t by di qj. So this expression should start to look pretty common, familiar, and that's got to be equal to the generalized force, qj. So let me do one of the examples from the problem set. I'm going to do problem 3.1, which is actually very complicated to do if you wanted to do with Newton's second law, and I encourage you to try. So I'll work through problem 3.1, and then I'll let you, for the assignment, work through problem 3.2. Okay? So let me do problem 3.1, and let's start a new page. So it's a deceivingly complicated problem, problem 3.1. So what we have is a ground on a wall. We have a massless rod. We have a second massless rod of the same length, and they're connected here by a hinge. There's a hinge down here as well. And then I guess here there's some sort of mechanism that's connected to the rod. And then there's a spring of spring constant K. So these rods have a length L, and they are massless. And so in this configuration where the rods are massless, at rest, this system can be described by this angle theta, and it's equal to theta naught. So this is kind of a suspension system. The point, let me label A, B, and C. So the point at C can slide back and forth along the x-axis. So let me introduce an origin here. So you see how it works, right? If you push down on point B, point A is fixed, so then point C will compress the spring. And when you're not pushing down on point B, the rods are massless, and we're told that the system sits at an angle theta naught. Okay, so that basically tells us what the length of the spring is when it's not under compression or tension. So the problem is, once you add a mass m, that's going to compress this suspension system, right? And then it's going to compress the string. And the question is, find theta when m is present. So I encourage you to try this with Newton's second law. And I would guess it would take you pages. So with the principle of virtual work, it's a little bit difficult to conceptualize when you don't have any practice, but then it's a three-liner. So if you go back to your notes, we had written down a procedure for solving these static problems with the principle of virtual work. So first we need to identify the number of degrees of freedom, and I've kind of already hinted at that, and there's only really one degree of freedom. That is, I can describe completely the state of the system by specifying just one number. Could be the compression of the spring, but I'm going to choose the angle theta. Okay? Next, we need to identify the forces on the system that can perform virtual work. And that's not necessarily trivial, but remember the whole point of this was that we can do we can ignore the internal forces. So if you think of the two connected rods with the hinges, you can think of that as a system, and the rods clearly are exerting forces on each other, but those are all internal forces. So the forces that really can do virtual work are the external forces that are applied to the system in this case. And so we have two such forces. We have the weight of our mass, and we have the force from the spring. So that we can apply the principle of virtual work and get that delta R term. So if I say the weight of mass m, call that F1, and let's say it's applied at position vector R1, and force F, so we'll call it F2, or the force from the spring, let's say it's applied at position R2 vector. So the slightly annoying thing here is that we need to know the magnitude of the force F, because the force from the spring, of course, the magnitude of it depends on the position of the system. And that's why you'll find Newton's second law very tricky. So we know that when theta equals theta naught, then that force is 0, right? That's when m is away, and then the spring is at rest. And the spring is necessarily at rest because the rods are massless. So we need to express, let me just include a little variable here, d, to be the compression of the spring. And so that's how much it's compressed from its resting position. So what I really want to do is I need to express how d depends on theta. So d equals 0 when theta equals theta naught, and d equals something bigger than 0 when theta is smaller than theta naught. So I can write d as 2L cos theta minus 2L cos theta naught. Right? So what color should I use? Let me use blue. This distance here from A to C, that distance is 2L cos theta, right? So that distance is 2L cos theta naught when the spring is not compressed, and it's 2L cos theta when the spring is compressed. So d is 2L cos theta minus 2L cos theta naught. Right? So now I need to write out R1 and R2 in terms of theta, because eventually I really need delta R1 and delta R2 in terms of delta theta. So let me write out the vector R1. So the vector R1, it has an x component of, well, it's going to have an overall length of L, and it's going to have an x component of cos theta, and a y component of sine theta. So that means that delta R1, so now I apply the chain rule, I want delta R1 when theta changes. So that's going to be L is a constant. Then I have minus sine theta delta theta x hat plus cos theta delta theta y hat. Let's do the same thing for R2. R2 is the vector, it only has an x component, so it's 2L cos theta x hat. And so if I take the variation of R with respect to theta, delta R2 is minus 2L sine theta delta theta x hat. If I write out my forces, let me call F1 the force from gravity, so that's minus mg y hat, and F2, the force of compression from the spring, is minus k times d, so it's minus k, or x hat, sorry, at the end there, so it's minus k times 2L cos theta minus 2L cos theta naught x hat. Alright, so now I have everything I need to calculate the total virtual work. So the total virtual work is F1 dotted with delta R1. So F1 only has a y component, which is minus mg, and so it's going to be minus mg times the y component of delta R1. So that's going to be minus mgl cos theta delta theta. And then plus F2 delta R2. So F2 is all in the x hat direction, so is delta R2. They're both negative, so when I dot product them, they'll be positive. So then I get plus 2KL sine theta, I'm going to put the delta theta at the end, then I have the 2L cos theta minus 2L cos theta naught delta theta. And so that's all got to equal 0, right? So since that's all got to equal to 0, then the thetas cancel. Or the delta thetas, I'm sorry, the delta thetas fall off. I can divide all the terms by an L, because the second term would have an L squared, right, and the first term has an L. So if I divide that out, I have minus mg cos theta plus 4kl sine theta times cos theta minus cos theta naught. And so that's equal to 0. And that turns out to be not such a trivial equation. If I divide sine theta out, so I divide every term by sine theta, then the first term is, and I'll bring the mg cos theta to the other side, so I have mg cosine theta over sine theta, which is cotan theta. So that's got to equal to 4kl. So now the sine theta is canceled, or divided out, times cos theta minus cos theta naught. If I want to put all the thetas on one side and the theta naughts on the other side, I have mg cotan theta minus 4kl cos theta equals minus 4kl cos theta naught. And so that's just a recursive equation, and it's you can't solve it analytically. So it's really only, I wrote it out carefully, but this is about 3 or 4 lines worth of real work. And so you can see by the shape of the equation that you ended up in the end, that doing this with Newton's second law is presumably going to be complicated. And remember, Newton's second law, you're going to have to put all the forces in, everything at point A, B, and C. Whereas with the principle of virtual work, you only care about 2 forces. Any questions about that? All right, so I encourage you to go back in the notes to look at there's at least 3 or 4 examples on applying the principle of virtual work with the procedure, and then I'll give you maybe 10 minutes to have a crack at problem 3.2. So of course, I know that problem 3.2 you can solve easily with, well, anything. You could have done that in, I guess, middle school is what's before high school in America. So this is a middle school problem. But you won't get any marks on the assignment if you don't solve problem 3.2 using the principle of virtual work. So problem 3.2 is just a lever problem. It's super trivial, and I'll give you one hint. In order to set this up with the principle of virtual work, I would draw the system so that it's not horizontal. So that gives you a clue maybe as to what you could use as a good generalized coordinate for this. So we'll give you 10 minutes or so, and then Michelle will help you get started on problem 3.3, which is also on the assignment. Of course, feel free to ask questions during the 10 minutes or whatever.
So,
Give you permission.
yeah.
Okay, so Any questions then on problem 3-2? You probably didn't have time to finish it. But hopefully enough to get started and see if you might have issues. Oh, do you want to do it online?
Yeah, I actually do. That would be better.
That way you can practice more on that one. Okay, so I'm going to let Michelle get you started on problem 3-3. This is pretty straightforward. You just try not to push the buttons while you're writing. Yeah, I think it's going to come naturally.
Okay. So can you guys hear me okay? Hello? Anybody? Oh, good. Thank you. Appreciate that confirmation. So the really cool thing about 3.3 is you can express the kinetic energy in general coordinates. So if you go to equation 3.29 in your text, equation 3.29, that tells you that AJK is equal to 1/2. We take the sum over n, I equals 1. Del R I over QJ, del RI over del QK. So we start with knowing that the kinetic energy is, I believe this is actually the equation 3.29, what I'm writing right now. Are there any questions here? Okay, yes, yes, yep, good, good, okay. Glad to hear it. So we need to expand. A little bit tricky, so I'm going to go ahead and do at least the first line for you. Oh, what happened? I touched something I shouldn't have. Swipe from the right. From the left. Okay. Oh, this is J. J equals 1. And R del Q J. This is a Q dot. Be sure to keep track of your Q dots. T. Then we also have another sum. You guys may have learned in math that you always use a different index when you have a different sum. Q dot K plus del RI. Okay, this is no surprise to any of you as I graded your last assignment, and I know this is no surprise to any of you, but just be really careful when you start doing your multiplications. So, okay. So I'm going to go ahead and give you one more line, and I hope this isn't too boring, but I think that it gives you a good place to check. I do want to see all your work. Don't jump in and say I went over it so you start from here. I would not like that at all. As we talk about likes and dislikes of graders, I can tell you right now that if something is a whole point and you draw a really nice picture and you label the picture thoroughly, that's probably worth a 1/4 point straight up. Okay, QJ Okay, I'm running out of room. So if it's all the same to you, I'm going to do that. That is a plus. Now, when I worked on this problem last night, I can tell you the cool trick here is right here. We know that if j is equal to 1, k is going to be equal to 1 as well. So as long as j and k are the same, then these two expressions are actually the same, because the only difference between them is the index, and the indexes are in fact the same. So keep that in mind when you go ahead and do your work on your own tonight. And then I wanted to let you know how the format should look. So basically, the form should look something like this. And this coefficient right here is going to probably look something like these coefficients here. And then, of course, you know the dot product, the dots. And then the coefficient b should also be a combination of these partial differential equations. So any questions? Well, with no questions at hand, I am going to move on to 4A. I love these. This is my favorite part of the whole class.
Should we let them work on this for 5 minutes?
Oh, sure. We can let you work on that for 5 minutes. Probably we'll have it pretty much wrapped up in 5. Just be careful. Don't be in a hurry. Does this page just go on and on?
Nope.
So this is actually the end of my page, and I'd need a new page.
Yeah, you would press the plus.
Okay, I think I can get 8 on here, though.
Scroll back up.
Oh, sure.
Yes. Push the top button. When you talk, you
There we
can
go. Yep. Someone can't read the denominators in the second and third summations. Okay, so that's a del Qj, and this is a del T, and this is a del Qk, and that's a del T. Did that help, Shane? All right, everything is a positive number. So we have, starting in this line, this is a positive, this is a positive, and they are being multiplied. And then we expand, so this is a positive, this is positive, and this is a plus sign. Did I answer your question? Yeah, no worries. I mean, it's hard to read people's writing, trust me. I read all of your guys' writing this last week, and I gave everyone a benefit of the doubt to the best of my ability, and just try to make things clear, and if you find yourself scribbling, just put a line through it and start again. I know it costs paper, but it's better to see, and I appreciate that, so don't worry about asking for clarification. It's probably time for us to move on to 4A. And like I was saying, this was absolutely my favorite part of the course when I took it, because I always wondered how on earth I was supposed to know the different coordinate systems and their values. So I became a consummate knower of the front covers because it was very confusing. And then one day Dr. Robert came in and he explained where all this came from, and I was so pleased. And I have to say that, you know, it takes more than one or two times, at least it does for me, before I'm any good with them. This is a dot. I'm just writing down our kinetic energy expression in Cartesian coordinates. You all are familiar with that. Now we need to go to polar. And I love pictures. Picture is worth 1,000 words. And it's worth at least a quarter point. So draw pictures. Z, Y, and X. So here I am on the rim. That's my point. And you know the Z direction is unchanged. Where we're at around the cylinder is phi. Now I realize some of you mathematicians are going to argue with me. Physics rules. It's phi. And this is our R. So what I'm going to do then is I'm going to put a projection down. This is R as well. There should be a line over it, but I think it just makes us get confused because I didn't draw big enough. And then in this direction, of course, is our theta. So I'm going to change colors. If this is theta, and I want to know what my y coordinate is, clearly it's a sine. So y is going to be equal to r sine phi, because phi is how far around we went. Yes. And our x come on, our x is clearly the cosine. And z is unchanged. Are there any questions at this point? Okay. Then the next step in our progression of doing things in a reasonable order is to take the first derivative of x. So that would be, oh, come on now, right, r dot cos minus r sine. Are there any questions about this? Then I will leave the rest of the derivations to you, and I will concentrate on x dot squared. Now, I'm old school. I like to write everything out. Again, I know it costs paper, but it's easy to follow my work. And when it's easy to follow someone's work, they usually get a benefit of the doubt. So I'm going to do an r dot squared here and a cosine squared. I'm going to do kind of a shortcut here because these are the same terms. I know that I have two of them. And personal preference causes me to put them in a particular order every time. I don't demand that of you, but I recommend that you find your own style and you put them in the same order for yourselves. Did I do that correctly? I think so. Any questions? Now, in polar coordinates, it's not too difficult to keep track of this, but I can tell you in spherical, which we're going to do next, it is. So what I would do is I'd tabulate these, and what I mean by that is I would collect all of my r dot terms, all of my, let's see here, where am I? All of my theta dot terms, probably r squareds, theta dot squareds, phi dot squareds, and all of my cross terms, r dot, theta dot, r dot, phi dot, theta, phi dot, and then see if the components cancel or I have to keep them. And so that's kind of how you handle a lot of data. I'm going to add a page, and we're going to start with 4B if there are no questions. I could probably give you maybe 5 minutes to work on this and see if questions come up. All right, that might not have been a full 5 minutes, but I want to not chintz you on Dr. Martin's one, so we're going to go on to 4B, and this is the spherical coordinates. And I admit my drawing isn't as good in spherical coordinates. You can look this up online, and I recommend that you do, because if you look this up online, you will find very, very nice diagrams showing are projected in the different directions. So I'm just going to try to describe this. If we're going down, we have the phi. So that's going down from like this North Pole thing. And then if we're going around, we're describing where in the sphere we are laterally. That's phi. Sorry, I'm doing my pet peeve. Phi. And that's why theta goes from 0 to pi, and I'm going to write this backwards, but you know what I mean. And phi goes from 0 to 2 pi, because phi goes all the way around the sphere, and it doesn't make any sense to go all the way around the sphere in theta, because I just end up with a negative. So that's why it's 0 to pi. You can look these up in the front of books, and they are very prevalent, which I am thankful for. Your x is r sine theta cosine phi. Your y is r sine theta cosine. Or sorry, not cosine. It's actually sine. You can remember that because, come on. Y has two sine terms in it, and then z is our cosine theta. And just like before, the first thing we do is take the first derivative. So that part's easy. Then we keep r the same. And I'm actually going to do an aside here. This can be a little bit tricky. So asides rule. You know I'm going to take the derivative of this, and you know it's the product rule. So I'm going to take the derivative of the first times the second plus the first times the derivative of the second. And now that I've done that, I'm going to take the whole thing, going to multiply it by the first, and just for completion, hopefully so there's no confusion, I'm going to write the whole thing out.
usually pretty good at getting all the bad things and happening that doesn't work very good things.
Okay, and then of course, now that I have three terms, taking x dot squared can be a little bit tricky.
That's a good thing, actually.
I'm not going to do that here, but I would recommend that you set it up so that you turn your paper long ways and you write out all the terms. And I'm going to run out of room, but you know what I mean. Yes? I hope so. If you do this long ways, then you'll have room on your paper to work all of this out and then again tabulate. And what I mean by that is you collect all of your x dot squared terms, all of your y.
R dot.
Hmm?
R dot.
R dot. Right you are. All of your r dot squareds, all of your theta dot squareds, all of your b dot squareds, make that right. That's a single dot. And then your cross product terms. Are there questions? Well, if there are no questions, I look forward to seeing this assignment. If you're running late, please contact Dr. Martin. I'd rather grade a whole assignment than half an assignment, even though half an assignment takes less time. So please do contact us if you need a little extra, and he can give you extra time at his discretion.
If you have a valid reason. Okay. Right, so I wanted to, there's three more problems on the problem set, number 5, 6, and 7, that are all applications of D'Alembert's equation, which we haven't really done so much for physical systems. We've done it for a few simple examples in the notes. But I'll encourage you to try 3-5 by yourselves. It's not due on the assignment, so you're probably going to try it, but it's easier because it only has 1 degree of freedom. I was going to do as an example 3-6, which has 2 degrees of freedom, much like 3-7, which you're supposed to hand in. So we're kind of running late, but I will try to squeeze in the whole of example 3-6, and then if you have to leave, you know, it'll be online. So problem 3-6 is one that we've already seen actually in assignment 1, where you were asked to use Newton's law to figure out the equations of motion. And here we'll do it with D'Alembert's principle. So you have a mass m1 that can slide along the x-axis, and then you have a mass m2 that's hooked by a spring to mass m1, or it's attached by a spring. The spring's have individual spring constants. So the second spring has a spring constant K2 and a rest length of L, whereas the first spring has a spring constant of K1 and a rest length of L. So the same rest length but different spring constants. The mass M2 can only, it's not a pendulum, so it can only oscillate up and down. So of course it's going to move right to left when M1 moves right to left, but M2 cannot swing. So you can imagine maybe there's a rod or like a piston, and M2 is on a piston with a spring. Okay, and everything is massless except the masses. So the goal here is to use D'Alembert's equation or D'Alembert's principle. And so let's just write that down to remind ourselves. D'Alembert's principle is that d by dt of di t by di qj dot minus di t by di qj is equal to capital Qj. So lowercase qj's are the degrees of freedom, and capital Qj are the generalized forces. So we need to identify the number of degrees of freedom. So there are 4 possible degrees of freedom. So we have 2 masses that are constrained to be in the plane, and so those degrees of freedom would be x1 and y1, the x and y position of mass 1, and x2 and y2, the position of mass m2. We have 2 constraints though. One constraint is that the x position of mass 2 must equal the x position of mass 1, because it's always underneath it. And the second constraint is that mass m1 is really constrained to the x-axis, and so y1 is always equal to 0. So we really have just 2 degrees of freedom. So you can now choose, of course, the degrees of freedom that you want. And an obvious choice, I guess, would be x1 and y1, or x1 and y2, right? So x to describe the position of mass m1 along the x-axis, and a y to describe the displacement of mass m2 below the x-axis. Okay. So instead of that, because I have springs, and you don't need to do this, you could do it a different way, but I'm going to choose different coordinates. So I'm going to choose generalized coordinates q1 and q2. I'm just going to call them q1 and q2. And I'm going to define q1 to be x1 minus L. And I'm going to define q2 to be minus y2 minus L. So Q1 is really just the extension of the spring for mass M1. So if I were to draw Q1 up here, this would be the Q1 axis with positive to the left and negative to the right. Positive to the right and negative to the left. And then Q2 is the same thing. It's the net displacement of the second spring. And then just to make it interesting, I chose Q2 to be positive downwards and negative upwards. Right? That's why you have a minus y2 in there. Okay, so those are the coordinates that I chose to be my generalized coordinates. So now we need to write out the kinetic energy in terms of those coordinates, right? So the kinetic energy, so we need T in terms of Q1 and Q2. So the kinetic energy, very naively, is just a half m1 times x1 dot squared plus y1 dot squared plus a half m2 times the kinetic energy of the second particle, which is x2 dot squared plus y2 dot squared. But now that's in terms of x1, y1, x2, y2. We really want that in terms of our generalized coordinates. So we need to write out the transformation between the generalized coordinates and the Cartesian coordinates. So x1 is easy. It's just q1 plus L. x2 is equal to x1, so it's also q1 plus L. y1 is 0, and y2 is minus q2 minus L. So that allows me to calculate the x1 dot, which is what I need for the kinetic energy. So that's d by dt of x1, which is d by dt of q1 plus L. L is a constant. This is property of the spring. So x1 dot is simply q1 dot. And that makes sense, right? q1 is our displacement from the origin, but the speed in the q1 direction should really be the same as in the x direction. It doesn't matter. The speed in the x direction is independent of where the origin is, and q1 is just the x-coordinate with a different origin. So that makes sense. x2, of course, is going to be the same, so x2 dot is also q1 dot. y1 dot, well, d by dt of 0 is 0, and y2 dot is going to be minus q2 dot. And again, that makes sense because y2, q2 is positive in the downgoing direction, whereas y is positive in the upgoing direction, so that's why you have a change in sign there. So putting all this, we can calculate the kinetic energy is now a half m1 times x1 dot squared, which is q1 dot squared, plus a half m2 times x2 dot squared, which is q1 dot squared, plus y2 dot squared, which will be q2 dot squared. So we have now what we wanted, the kinetic energy in terms of our generalized coordinates. So what we further need is we need now to calculate the generalized forces, the capital QJ term. So QJ, the generalized force, is the sum over all the forces of that force dotted with di Ri by di Qj. And so remember, Qj, in this case, there's only two of them, Q1 and Q2. So what we need is to identify what forces we have and where those forces are applied. So we have three forces. And again, it's forces that can do virtual work, right? Because all the other ones end up canceling out. So we have the restoring force of the first spring, which I'll call F1. We have the restoring force of the second spring, which I'll call F2. And then we have the weight of M2, which I'll call F3. So let me write out those forces. So F1, in magnitude, it's K times Q1, right? That was the whole point of defining Q1. Its direction is in the x direction, and it's in the minus x direction. F2 is, in magnitude, it's, oh sorry, that's a K1, Q1, right, because they're different Ks. So in magnitude, it's K2, Q2. And if I look at my x and y axes, then F2 is in the positive y direction. And then F3, no surprise, it's minus mg y hat. Okay, so now we need to write out the vectors R1 and R2 and R3 for where those forces are applied. So the R1 vector is really just x1 times x hat, right? The F1 force is applied at the position of mass m1, and its position vector is x1 x hat. And so x1 is q1 plus L. So R1 is q1 plus L x hat. R2 turns out to just be the position of mass m2, right? That's where the second force is applied. So if I plug in my value for y2, that's minus q2 minus L in the y hat direction. And finally, R3 oh, I'm sorry. R2 has both an x and a y component, right? It's, let me just cancel that. R2 is x2 x hat plus y2 y hat, right? And so that'll be x2, which is equal to x1. So that's q1 plus L x hat. And then the y component of that is what we had, plus minus q2 minus L y hat. And so R3 is where the weight, or where F3 is applied, and that's applied on mass M2, and so that ends up being exactly the same location. So R3 is equal to R2. So I realize we're over time, so I'll just finish the problem because we're almost done, and if you have to leave, you can just look at it on the video. Okay, so we've set everything up now. The final thing that we need, though, is the di Ri by di Qj, and we have two different Qs. So let me start a new page. So what we need is di R1 by di Q1. So that's di by di Q1 of our R1 vector, which was Q1 plus L x hat. So di by di Q1 of that is simply x hat, right? Di R1 by di Q2, well, R1 doesn't depend on Q2, so that's simply going to be 0. Then we need di R2 by di Q1, so that's di by di Q1 of Q1 plus L x hat plus minus Q2 minus L y hat. And so di by di Q1 of that is again simply just x hat. And then di R2 vector by di Q2 is di by di Q2 of the same thing. And so that is going to give us just minus y hat. And of course, these are the same for the R3 vector, since R3 was equal to R2. So we have now all of our ingredients. So now we can calculate the capital Q's. All right, so we have Q1 is the sum from I equals 1 to capital N of Fi dotted with di Ri by di Q1. So the di Ri by di Q1 are the terms that we just have up here, right? So there's 3 of them. So let's write out explicitly. So the first term is F1. So F1 is minus KQ1 x hat. We have minus KQ1 x hat dotted with di R1 by di Q1. So that's x hat. Plus F2. F2 is K2Q2 y hat. And that's got to be dotted with di R2 by di Q1. So di R2 by di Q1 is x hat. So that's going to be 0. And then the last term is F3. F3 was minus mg y hat. And that's again dotted with di R2 or di R3 by di Q1. And that's again equal to x hat. So that's dotted with x hat. So ultimately, the generalized force in the Q1 direction, the last 2 terms are 0. And so that's equal to minus KQ1. The second term now, we need Q2. That's defined to be the sum from I equals 1 to capital N of Fi dotted with di Ri by di Q2. Alright, so I'll highlight the fact that that's where the indices appear. Because it's easy to get confused about what it is you're summing over. So again, I'm going to do the same thing now. So F1 was minus KQ1 x hat. And that's got to be dotted with di R1 by di Q2. Well, di R1 by di Q2 was just 0. The second term is F2. F2 is K2 Q2 y hat. And that's got to be dotted now with di R2 by di Q2. So di R2 by di Q2 is minus y hat. And finally, the last term, F3, which is minus mg y hat, that's again dotted with the same thing, which is di R3 by di Q2. So we end up with, the first term is 0. The second term is minus K2 Q2. And then the final term is mgy. Right, sorry, just mg. There's no y there. So we now have everything to put into D'Alembert's equation. Remember D'Alembert's equation, d by dt of di t by di q j dot minus di t by di q j equals capital Qj. So t, remember, was, let me rearrange, this is what we found for t up here, a half m1 q1 dot squared plus a half m2 q1 dot squared plus q2 dot squared. Let me group the terms in Q1 and Q2 together. So that's equal to a half M1 plus M2 Q1 dot squared plus a half M2 Q2 dot squared. So now let me do D'Alembert's equation for Q1. So instead of a Qj, I have Q1, right? So I have d by dt of di t by di Q1 dot. So if I look at t, the term in Q1 dot is a half m1 plus m2 Q1 dot squared. If I take d by dq1 dot of that, I get, so the 2's cancel from the derivative, and I have an m1 plus m2 times Q1 dot. T itself doesn't depend on Q1, right? It only depends on Q1 dot. So there's no term di t by di qj. And so that's got to equal to q1. Capital Q1 was minus k q1. So if I carry out the derivative with respect to time, m1 plus m2 is a constant. And so I get m1 plus m2 q1 double dot equals minus k q1. Let me do the same thing for q2. So I have d by dt of di t by di q2 dot. So if I look at t, the q2 dot term is the last one, a half m2 q2 dot squared. If I take d by di q2 dot of that, I get m2 q2 dot. And again, t doesn't depend on q2, it only depends on q2 dot. And then that's got to equal to the capital q2. The capital q2 we found was minus k2 q2 plus mg. So sorry, that mg should really be m2g, right? I think I forget it everywhere. It's the weight of the second particle. Second mass. Okay. Carrying out the time derivative, I get m2 q2 double dot equals minus k2 q2 plus m2 g. And so those are the equations of motion for my generalized coordinates q1 and q2. And that makes total sense, right? The first one is just the equation of a simple harmonic oscillator, but of mass m1 plus m2, right? Because the spring on mass m1 has to pull back and forth both masses, right? So it's as if you had a one-dimensional simple harmonic oscillator with a mass m1 plus m2. And then the second equation is just a simple harmonic oscillator with gravity. Right, any questions about that? So procedurally, problem 3.7 is exactly the same. You have to do the same steps of identifying the forces and everything. And in this case, there will be only 2 degrees of freedom, and you can use, for example, r and theta or something like that. Sorry for going over time like that. Why didn't the second part of Q2 not change? I'm not sure what you mean. Put the corner of the left hand. So we're only taking the time derivative of the kinetic energy term, right? On the other side of the equation, we have the generalized force component. And so the generalized force component was just found by using that sum over Fi di Ri by di Qj. I'm not sure if I answered your question or not. When I took the time derivative and going from here to here, I added a dot on the Q1, right? Is that what you mean? So it has changed because there's an extra dot on Q1 and Q2. Does it change how we interpret the answer? Well, the answer is really basically a function for Q1. Sorry, so the answer, the red box, is a differential equation for Q1, right? I haven't solved that. So the boxed equations, these are actually uncoupled ordinary differential equations. So, but they are the differential equations that give you Q1 and Q2 of t, right? So the first equation, for example, oops. The first equation is like m1 plus m2 times d squared q1 by dt squared minus or plus kq1 equals 0. So it's a differential equation. So the equations of motions are differential equations. I don't know. Does that answer your question, or? Okay, sorry. Sorry for not understanding him in the first second. Any other questions? I assume you're typing another question. So you have to be very careful in how you're consistent with this, right? But the y-axis is positive going up, right? And when I wrote the vectors, I wrote the vectors in the x and y coordinate system. Because Q1 and Q2 I really prefer if they're just scalars. So I chose Q1 and Q2 so that I would always have it that if the spring is extended versus compressed, so if the spring is extended, then the Q variable is positive. That way, when I write, when I make my diagram and I write these forces here, I don't have any doubts that the magnitude is truly K1, Q1, and then I can assume that I've drawn the springs in extension, and then I can assign the direction of the force. So you have to be very, very careful. That's right. So if I compress the spring, now Q2 would be negative, right? Let's look at F2. If I compress the spring, Q2 would be negative. So K2, Q2, Y, F2 is still K2, Q2, Y hat, right? But if the spring is compressed, then Q2 is actually a negative number, and F2 would be pointing downwards. So it does work out. But I made it so that I wouldn't have to think about it when the springs are in extension. But it's very easy to mix up. In fact, the first time I did it, I screwed up the signs as well. Okay, so I'll encourage you to post further questions on the discussion forum, and we'll leave it at that for now. Thanks, everyone. I'll see you all talk to you all on Tuesday.